All right, let's jump right in. Today, we're going to tackle a really beautiful problem from the world of competitive programming. It's called insolvable disks, and trust me, it's one of those puzzles that looks like one thing on the surface, but is something completely different underneath.
So when you first see it, it seems pretty straightforward. You're asked to place a bunch of disks on a line. Right away, your brain goes to geometry, right? You're thinking about their centers, their radii, and how to make sure they don't overlap. It has all the makings of a classic geometry puzzle.
But, and this is the best part, here comes the twist. All those geometric rules, the touching and not overlapping stuff, it turns out they're just a clever disguise for a really simple and elegant algebraic pattern. And yeah, you guessed it, cracking that pattern is the entire key to solving this thing.
So here's how we're going to break this down. First, we'll define the puzzle properly. Then, we'll look at why the most obvious approach just doesn't work. After that, we'll dig into the algebraic chain reaction that makes this problem tick. Use that to build a super efficient solution, and then we'll wrap up by looking at how this whole thing is a beautiful example of geometry turning into algebra.
All right, first up, a geometric puzzle. Let's really get into the nitty-gritty. What are the exact rules of the game here?
Okay, so here's the setup. Imagine you're given a bunch of points on the x-axis. These are going to be the centers of our disks. Now for each one, you have to pick a radius, and it has to be greater than 0. The real challenge, the goal of the whole thing, is to choose those radii so that you get the maximum number of adjacent disks just barely touching, tangent, but without any of them overlapping. Okay, so now let's talk about why our first instinct, what we call a greedy strategy, totally hits a wall. A greedy approach is when you just make the best-looking choice at each step and hope for the best. In this case, it'd be like, okay, I'll just pick a radius for the first disk and see where that takes me. But spoiler alert, the obvious path here is a trap.
So, how would you try to solve this if you were just winging it? What's the most straightforward, greedy way to go about it? Yeah, you'd probably think exactly that. Let me just start at disk 1 and make my choices as I go.
And on the surface, this logic seems totally solid. You pick some valid radius for the first disk, R1. Okay, simple enough. But if R1 is going to touch R2, then the radius of R2 is now completely locked in. And if R2 touches R3, well, R3 is now locked in too. It just feels like a simple domino effect, a chain reaction down the line.
And this is where the whole thing just completely falls apart. You can make what seems like a perfectly good choice for that first radius. But as that decision cascades down the line, bam! You might find that, say, the 10th disk is forced to have a negative radius. And a negative radius isn't a thing, right? So that's impossible. The entire chain you've built is now totally invalid.
Okay, so the greedy approach is a dead end. Why? Because a choice you make at the very beginning can have these crazy, unforeseen consequences way down the line. That's a huge clue. It tells us we need to stop thinking one step at a time and instead look for the hidden mathematical pattern. Let's actually dig into the algebra of this chain reaction.
All right, let's get into the equations. To make things easier, let's call di the distance between the center of disk I and I plus 1. Super simple. Now for any two disks to be tangent, their radii have to add up to that distance. So ri plus 1 has to equal di. That means if we know r1, then r2 is totally determined. It has to be d1 minus r1.
Okay, that's R2. Now what about R3? Well, its radius depends on R2. So let's just substitute that expression for R2 we just found. We get R3 equals D2 minus the whole D1 minus R1 thing, and hey, look at that. When you expand it out, you get R3 equals D2 minus D1 plus R1. You see that? We're starting to see a pattern. Plus, minus, plus.
Let's just do one more, for R4, just to be absolutely sure. We substitute our new formula for R3 in there, and what do we get? R4 equals D3 minus D2 plus D1 minus R1. Okay, yep, the pattern is crystal clear now. Any radius, Ri down the line, is just this alternating sum of the distances between the centers, and then at the very end, it's either plus or minus our original choice, R1. And this is the absolute crux of it. For every single one of those radii to be positive, it puts a new rule, a new constraint on our very first choice, R1. Think about it. For the odd-numbered disks, the formula has a plus R1. To keep that radius positive, R1 has to be greater than some value. That gives us a lower bound. For the even disks, it's minus R1. To keep those radii positive, R1 has to be less than some value. That gives us an upper bound.
So, with this insight, we can build a ridiculously efficient algorithm. We're talking linear time, O of n. The big idea is this. Instead of trying to pick a single value for R1, let's just keep track of the range, or the window, of all possible valid values for it. And as we add each new disk to our chain, that window is going to get smaller and smaller.
Okay, so let's quickly peek at the variables we'll need to code this up. We'll have ands for our answer, which will start off assuming everything works. S will be our running alternating sum of distances. And then the most important ones, L and R for the lower and upper bounds. These two define that window of possibility for our chain's starting radius.
So here's the core idea of the algorithm. We're just going to loop through the disks one by one, and for each disk we update our running sum S. Then, depending on whether it's an odd or even disk in the chain, we use S to tighten our L and R bounds. So this range from L to R is basically our safe zone for a starting radius, and with every single disk we add, the constraints get tighter, and that safe zone just shrinks.
Okay, but this brings us to the most critical question of the entire algorithm. What happens if that window closes completely? What does it mean if our lower bound, L, actually crosses over and becomes bigger than our upper bound, R? What happens when our safe zone just vanishes?
And the answer is just so clever. If L becomes bigger than R, it means there is no possible starting radius that can make this entire chain work. The chain is literally insolvable. So what do? We have to break a link. We subtract 1 from our answer because we just lost a tangent pair. And then we just reset everything, L, R, and S, and start a brand new chain right from where we are.
So let's just take a step back and really appreciate what just happened here. The takeaway is beautiful. We started with what looked like a super messy geometry problem, right? Placing circles, checking for overlaps, and we ended up with a simple, elegant algebraic check.
I mean, it's just a perfect example of how the most beautiful solutions often transform a problem into its simplest possible form. We took this complex geometric puzzle and boiled it down to a much, much simpler question. Can we find a number that fits inside a window that keeps getting smaller? By finding that hidden system of inequalities, the solution becomes almost trivial, and it runs in that gorgeous, efficient linear time.
And really, that just leaves us with one final thought to chew on. How many other problems out there that look totally impossible on the surface are just hiding a simple, beautiful structure underneath? Finding that hidden structure, that's often what problem solving's all about. Thanks for diving in with me on this one.